All right, let's get started. I'm using the ambient microphones in the room today because technology is deciding to fail me since I came back from my conference, getting a slow start and whatnot. Let's review logistics and the schedule and make sure everybody's clear as to what's going on. So we are getting down to the wire in terms of finishing up the class. But fortunately, we don't really have a whole lot else to discuss other than we're going to finish development length today, and then we're going to get into columns and beam columns, and that's going to be our final topic. And the thing with columns and beam columns is the theory behind columns and beam columns is about the easiest stuff you've ever heard. There's just a lot of nitpicky little details with columns that you have to check. So nothing that's technically complicated. It's really simple. The outstanding stuff in the class is currently being graded, so that's exam 2 and homework 7. My goal is to get you the exam back on Monday because I've got the weekend. So I'll be honest, I have some outstanding stuff for senior design that's due for them as well, and it is a little more time sensitive. So I will admit my push is to try and get them moving forward, but I should be able to grade your exam as well. Okay, homework number 7 is really not a time-sensitive issue because it was covered on the exam and you all have the solution and everything. As for what's available online and what you have the solution for everything except for homeworks 8 and 9. Now homework 8 is due next Wednesday, so Monday come prepared to ask questions because that's the day before it's due. Then you will get homework 9, which is the homework on columns and beam columns, and it's due Friday, May the 3rd. And we're just going to keep on trucking throughout this week, throughout next week. We have that makeup day listed in the schedule during dead week. We may need to use it, we may not. We'll just see where we're at. I'm going to try and get you to a point where you don't need it, but we will see. I have 2 other items I'd like to discuss. First off, capstone. Next semester, or the next year's sequence of Engineering 452. I sent emails, so there's been a series of emails that you all should have received. One of them was an email that came from me that was an analysis of what prerequisites that you needed in order to register for capstone. So, a lot of you have said you didn't need anything. Some of you have said you needed a design course here or there. And then like I said, I was at that conference the past few days, but while I was there, I had some emails drafted that should have registered most of you for the class. So you should be in the class, and if you're not in the class, you should know why. And it boils down to, for the most part, one of 2 things. There is an enrollment cap in 451 that needs to be augmented, that's currently being in the works. So if you're not in capstone and you need to be, and the issue is project management, just hold off, and when you get into project management, just email Lee, and she should sign you into capstone. The other is there's a couple of you that had overloads that were over 18 hours, and there's just a simple form you need to sign if you've got to deal with that. And that's it. So other than that, you should be squared away. Any questions? Okay. Next item, course evals. So I'm going to do the same thing I've done in previous years. I haven't set it up yet, but if you do your course eval, again, you can rake me over the coals, say I'm the worst professor you've ever had, but if you just do it and upload that image that says that you did it, that's 10 free homework points, okay? And that's added on top of what you've earned as your homework average. So can you earn a homework average over 100%? Yes, you can, okay? So just do it, and that's it. You can say I'm the worst professor ever, I just want to see that you did it. Sound good?
Do we email it to you, like a screen capture?
No, upload it. Cause Steel design, I'm not going to be able to keep track of it, which is why if I'm going to use Blackboard for Steel, I'm going to use it for in here as well. So there'll be a little thing where it just says upload a JPEG. You just screen capture, upload it, you're done. So, but yeah, please don't email it to me because I will lose it. I would say, if it was just us, it probably wouldn't be a big deal, but with the 48 people we have in steel design, I will lose it. I can go ahead and tell you. And so I don't want you to not get your bonus points because I missed an email. So. Sound good? Okay, so we have one final example on development length, which is on hooks. This is going to be really short. and then we're probably just going to spend the rest of the time talking about columns. So just so everybody's clear, we were talking about development length when we got back, and development length was the idea, if you have an element, a rebar, what have you, how far does that piece of rebar need to be embedded into a mass of concrete in order to develop its full capacity, its capacity being at what? Now, we have a pretty straightforward plug and chug expression. Let me go back a few slides. For straight bars, and that's plug and chug. But I think it's fair to say that the mechanics change when you stop looking at straight bars and you start looking at bars that have been bent, i.e. hooks. Okay. Now, if you're using a hook, that does decrease the development length quite a bit, and it does make the analysis a little bit more straightforward because the equation shrinks a bit. Why does it shrink a bit? Well, it shrinks because top bar location, like the location of the bars, stop really mattering when you're looking at hooks, and also the bar size stops mattering when you're looking at hooks, because the mechanics of how that bar is held into place by the concrete change. You're not looking at friction and contact between the concrete and the ribs of the rebar. You're looking at a whole different phenomenon. Now, what you find is that the epoxy, that does still matter, and using an epoxy-coated bar, that is still the same deal, so we do have to account for that. We have a new cover factor and a new confinement factor that we need to consider. Again, the simple case and the conservative case is just to take those values equal to 1. So that is still a viable option. Last time we went through the cover factor delineations, what's the deal with the cover factor, what's the deal with the confinement factor. The confinement factor is the one I think actually needs a little bit of an image to kind of explain what's going on. So I have that. Same reduction that we can apply before, and instead of belaboring the notes over and over and over again, this is really one of those topics where the best way to learn it is to just do it. So let's go ahead and do this example real quick. This is example 17. We're going to determine the length for the epoxy-coated bars shown. So we got a little bit more going on here. However, what I'm going to do to illustrate how the effect of using a hook, I want to be able to demonstrate how bending the bars could really help development length. We're going to do this problem twice. So one of the times we're going to do it, we're going to assume that it's a straight bar, and we're going to assume KTR equals 0, and then we're going to do bars ending in a 90-degree hook. And say for all of these bars, we're going to assume they're all top bars, which, I mean, that's pretty clear looking at the dimensions, because this dimension is larger than 12 inches. But we'll go through each of these one at a time. We're using 4 KSI, normal weight concrete. I guess I should put normal weight concrete here. And we're using rebar that's grade 60. So in the interest of making this simple, what I'm going to do is, where's my snipping tool? Let's snip this. If it's been a while since you've done these development length problems, and it's been a while since you looked at this, I'd argue this is probably one of the best examples that we could do, because we're doing straight bars and hooks all in one example. So there's a lot of coverage in this one particular problem. So let me drag that out a little bit. Now, there's a couple things though that are a little innocuous that we kind of need to figure out. So first off, I'm gonna also be a little lazy here. I'm going to go up a few slides. Let me see if I can, let's try this. How does that work? There's my equation for development length for a hook. Let me be a little lazier. And let's copy this. Okay, so what I've done here is I've put the equation for the development length of a straight bar and the development length for a hook on the screen so that I don't have to keep flipping back and forth and looking at them. And what we'll do is we're going to take each of these factors one by one, and we're going to start identifying them, okay? Now, before we get into this, okay, let's do a couple things. So, first off, we're going to assume that KTR is 0, so we don't have to really worry so much about that. Let's see if we can start chipping away at some of these values. So we have an Fy 60,000 PSI. So we have Fy 60,000 PSI. We have an FC prime of 4,000 PSI. We have a lambda of what? 1. Okay, all right. So a couple things that we've already got figured out. Now, here's one that might be worth some discussion. What's the bar diameter? Is it 1 inch? Why'd you say 1 inch? No. Well, hold on. So why does the number 9 have a diameter of 1 inch? The area of a number 9 is 1 inch. What's the diameter?
1.125.
1.125. So you're saying 9/8.
Yeah.
Okay, take the area of a circle that's 9/8 inches in diameter, and what do you get? I see you turning the stuff. You keep quiet. What's the area of a bar that has a 9/8 inch diameter?
Process. It's a long process.
Now break out that Casio FX 115 ES Plus. Yeah.
It's this pi r squared.
Yeah. Or pi d squared over 4. But it's not 1, is it?
No.
Okay. You're right. It's not 1. So what is the diameter of a number 9? Well, there's a couple ways you could figure that out. One way to figure that out would be to say, okay, the area of a circle is pi d squared over 4. Set that equal to 1. So you could do that. Or you could do what I do, which is be lazy, and recognize that if you go way back in the PowerPoint, down to slide 55, when we first started talking about rebar, if you go to slide number 65, I actually listed for each individual rebar the bar number, the bar diameter, and the bar area. Now, a number 9 has an area of 1 square inch, so the area of a number 9 is 1 square inch, but the diameter of a number 9 is 1.128.
I was close enough.
But think, it wouldn't have worked for like a number 11 or a number 14 or a number 18.
That's why we round.
No.
Will that be provided?
Yeah, you'll have, whatever stuff like that you'll need on the exam, you'll have it. But at the same time, I've already provided it on your homework, so I'm not going to give it to you again for homework.
Oh, I was just wondering if we were trying to do that on an exam or.
No. But I just want you to see where that value is coming from.
Yeah.
So does that make sense? Is everybody okay with that? So the D sub B is the diameter of a number 9, which is 1.128 inches. So I wanted to be clear that that value isn't 1. There's a reason why I set this example up like this. And I mean, there's a reason I just said, oh, by the way, what's the diameter of a number 9? And I can't begin to tell you how many students have said it's 1. And it's not. The area of a number 9 is 1, not the diameter. Okay? So it's a very easy mistake to make, and I want us to make that mistake here as opposed to on Celebration. Sound good? Okay. So now we got to start breaking out our factors. So let's start looking at our factors. So let's take each of these one at a time. So psi sub t. What is psi sub t going to be for this problem? asking you. One point three. So you're saying it's 1.3. I would like you to tell me. Hold on. So 1.3. I would like you to tell me why it's 1.3.
Because there's top bars that are farther than 12 inches away from the bottom.
So top bars, clear distance is greater than or equal to 12 inches. So that way we have a reasoning why it's there. Okay? Sound good? Somebody else is going to take psi e. So psi e, somebody else tell me. Somebody not in the front row. I want somebody back here. What is the value for psi e going to be? First off, what is psi e? Psi e is our factor for epoxy-coated bars. Is that value 1?
Nope.
It's not 1, right? There are some options. What are the two options?
Either epoxy coated with cover less than 3 dB or clear spacing less than 6 dB or other.
Cover less than 3 dB and spacing
Less than 6 dB.
6 dB. Okay, so option 1 would be this, and option 2 would basically be anything else. And if you're in option 1, what's your factor?
1.5.
1.5, and this would be 1.2. Okay, all right. All right, I'm better now. Okay, so let's see. So let's take each of these one at a time. Let's start off with cover. What is the cover for these bars? And the way that this beam is set out, they all have the same cover. That's why this problem is formulated like this. So what is the cover for these bars? The cover. Anybody remember what cover is? 2.5. It's the distance from the center of a bar to the edge, to the nearest edge. So from this bar to the edge, this bar to the edge, this bar to the edge, and so on and so forth, the worst case scenario is a cover of 2.5 inches. Is that less than 3 bar diameters? Yeah. What about the bar spacing? What is the bar spacing? 4.5 inches. Is that less than 6 bar diameters? Yeah. So we got really slick bars and not a lot of concrete in between them. So that means we are going to use 1.5. If you want a reasoning, epoxy-coated bars. And I'll say minimal cover spacing. Okay? Now, what about size of S? What's going on with size of S? Say it again?
Equals 1.
1. Why does it equal 1?
Number 6.
There we go. Now, for the purposes, yes.
On the epoxy one, as long as one of those is less than 1.5, right?
Yes, yes. You're right. Yes, sorry. You're right. You're right. Any one of, like, you have to meet, like, you have to essentially, like, the other one, if they're greater, you have to meet both of them to use 1.2. But if any one of these are met, then it's 1.5. You're exactly right. So if you had adequate cover but not enough bar spacing, you'd use 1.5. Or if you had adequate bar spacing but not enough cover, then you'd use 1.5. That's a fair question. Does that make sense? Everybody okay with that? Okay, that's good. Thank you for that. I appreciate that. That's a good clarification. All right. Let's take our equation for the development length of a straight bar Help me out. Let's look at this equation up here. What are we missing? CB, right? Now, remember, for you folks in steel design, not even the same thing for beams. And so, actually today in steel design, we're going to talk about nothing but C sub B. That's our whole topic for steel design today, and it's not the same. We're not even the same. Okay, so now we got to figure out C sub B. Now, I'm curious if anybody here can eyeball C sub B and tell me what the value is. 2.25. Does everybody see that? Remember, for any one bar, we take the minimum of 3 distances. How far it is to here, how far it is to here, and how far it is there. And it's that center spacing that's the worst, right? Or the smallest. From there to there is half that, so that's 2 1/4. That's the same distance, actually, for all of the bars here, okay? So theoretically, if you had weird spacings, you could have different development length for each bar. Although, in practice, it's not as big of a deal. Okay, so, do I have everything I need to plug into this upper expression? Yes or no? Now, anybody got a problem with me just plugging and chugging right now? You have a problem with me plugging and chugging right now. What is that problem?
You need to multiply the 1.3 by 1.5 to make sure it's less than.
There you go, exactly right. So there's 2 checks that we have to perform before we start plugging and chugging. So let's look at straight bars. So there's 2 checks. First off, we have this check, which is 1.3, 1.5, and that equals what? 1.95. Well, what's the problem with that? It's greater than 1.7. So what that means is we use psi t, psi e equal 1.7. So in the equation, we do not put in a separate value for this and a separate value for this. We just put in 1.7. In fact, honestly, if I was writing the equation, it would make it nastier, but the way that I would probably write the equation is I would say that LD is, and I'd have a big fraction, and I'd say, okay, 3 times Fy times psi s times dB. But instead of multiplying by psi t and psi e, what I'd probably say is it's the minimum of psi t, psi e, or 1.7. Like that's probably how I would write that if I was doing this in Excel land. And then there's something else I would do is on the bottom I'd say 40 times lambda times the square root of fc prime. And then I would probably say times the minimum of that ratio and what? 2.5. That would make the equation a little nastier, but it would also make it, I think, a little clearer, So, because that's actually what you're doing. Speaking of, let's do this second check right here. So, what is C sub B plus KTR over dB? What is that? Well, it's 2.25 over 1.128. And that equals what?
1.995.
1.995. And is that okay? Because that's less than or equal to 2.5. So therefore, the development length is, so we have 3 times 60,000 PSI. Then we have 1.7 times 1 times 1.128. Let me know if I forget something, because we got 41 square root of 4,000 PSI. then 1.995. Did I forget anything?
$63.4, 68.4.
Uh-oh, got a conflict. What was it?
68.4.
68.4 inches. Do I have a second on that? Okay. All right. So we'll say A, the development length was 68.4 inches. Now, there's a couple ways that we could improve that, but that's still pretty long, assuming we keep a straight bar. If we wanted to get really pricey and really fancy, we could galvanize our bars. Why would we galvanize the bars? Like, what's the purpose of galvanizing the bars anyways? Like, why are we using epoxy coated bars? Corrosion resistance. Well, if we galvanize them, we get the same corrosion resistance, but why is the advantage? Like, where's the advantage? Say it again. It's not as slippery. So we could probably galvanize the bars and be able to use a psi E of 1. That would be a way of fixing like our development length if we really didn't have the room. On top of that, we could try and start playing with the dimensions. Like maybe we could lower the bars so that they're not all top bars, but that's probably really unfeasible. This is probably a cantilevered beam. So if you start lowering the bars, you're really going to decrease the moment capacity, and that's probably not going to work either. There's one other way that we could reduce this development length, but we don't have all the information to do it. But there's one way we could reduce the development length.
It's AS required.
It's area steel required divided by the area steel provided. We don't know how much steel is actually needed. Like we put in 6 square inches, but it might have only needed 5 square inches. So we could reduce the development length that way. However, there's going to be a cap. Like there's going to be a point where we really can't do much. Okay? So let me show you what happens when you use a hook. It's kind of crazy. Now, here's the thing for the hook problem. We don't have any information about the cover or the confinement. Okay? In practice, that's really easy though. Just put a bunch of concrete around it and put a bunch of steel around it. But I want to just keep them to be 1 for now. Now, what's our expression for the development length of the hook? Here, I'm lazy. I'm going to copy this down. Just look at what happens. So on the top, we have 60,000 PSI. We have psi E is 1.5, 1, 1, then the bar diameter 1.128. We have 50, 1, 4,000 PSI. Just look at what happens. It's crazy. Remember, this is for psi C equals psi R is 1. What do we get?
32.1.
32.1. Look at that. It's insane how much that development length cut. Just by bending that bar. Yes?
Is there any difference in how you go about getting the development length for hooks? If it's 180 degree thing?
No. That's a great question. Is there a difference between a 90-degree hook and a 180-degree hook? No. Like, it's the same equation. The only difference is you might have a different value for these, and they're just lookups like we've been doing. So, yes.
How do we know how much is supposed to be, like what's like the turnaround point of the rebar, for instance? Like, how much we have vertically versus Cause I know it has to be in a certain length, like there's 32.1 inches inside of the,
Mm-hmm.
so the concrete, how much is vertical versus horizontal?
Okay, that part I don't understand your question. What do you mean vertical versus horizontal?
Like how much is bent versus how much is still straight, cause it's a hood.
Well,
It's like a certain amount that has to be actually bent based on the 32.1.
well, first off, I have a couple answers that would completely define the geometry, and we'll see if that answers it. So, when I say the developed length of a hook, I'm starting from the point where it embeds to the outermost dimension. So that's the development length. From here to here, or here to here. So we're talking about, if I can put it on the screen, we're talking about like from that edge to that edge, like inside of the red to inside of the red. That's the development line, okay? As for what defines the geometry, well, I mean, this dimension is 12 times the bar diameter. This dimension here is a function of the radius, and these are the radii depending upon the bar sizes used. Same thing for up here. So, does that kind of answer your question?
Yeah, that's what
Okay, everybody else okay with that? Now, I provided you absolutely no information about the cover. The cover would just be lookups from right here. Let me ask you a question. For this problem, what if psi c is 0.7 and psi r is 0.8? What's the development length come out if you use this? Like, just what happens? All you gotta do is multiply this times 0.7 and then times 0.8.
18 inches.
Second? That's a big deal, right? Have a very substantial reduction of your development length. And what if you use galvanized bars? What happens if you take that and divide it by 1.5?
12 inches.
See what I mean? Completely different story, right? So, this is 18.0 inches, and then if we had psi e equal 1, it'd be 12 inches. Does that make sense? Now, I want to go back to something we discussed at the very, very beginning to sort of make a point. Because I think now this point will become a lot clearer. Do you remember that the first thing, when we first started talking about development length, we said, okay, here's a beam, right? Here's a beam, and we're using 6 bars of reinforcement. So what we could do is we say, well, mu is WL squared over 8, and that's what we're designing for, but we have different moments across the span. And what we could say is, well, let's compute the moment capacity. Let's have a plot for what the moment diagram looks like. Let's compute the moment capacity for 6 bars, 4 bars, and 2 bars, figure out what the cutoff points were, and this is what we could do to optimize the section. But the problem is, right here, we're cutting off the bar lengths. We're cutting them off at the theoretical point where we don't need them anymore. But really, we can't do that. What we could do is cut them off at this distance plus a development length. And this distance plus a development length. Does that make sense? Here's the problem though. Those development lengths tend to be so damn long anyways, we might as well just use that. Does that make sense? Everybody okay with that? I just wanted you to be clear as to why we don't do this. And it's the reasons development, yes.
So for that top development length that you just drew,
Yeah,
so that one isn't even going into the support. Is that what you're saying here?
that's a great point. It very well could. It very well could. And the way that you handle that is you just put more steel there. And that's what we've done here. That's a great point. It very well might not, the development length very well might go out here. And then you're like, well then what do? Well, you just have more bars, which is why we end up just extending it a long way anyways. That's a good question. Does that make sense? Everybody okay with this? I'm getting into some details here, but I really want this to make sense.
Well, just thinking of it from a practical standpoint in the field too, it's a lot easier just to spec 5 bars of the same length.
You're right.
Just different lengths.
You're right. Now, let me be clear, there are a lot of things that we could talk about when it comes to bar development that we just don't have time to discuss. For instance, if you have a beam that's 50 foot long, have you ever seen a 50 foot long piece of rebar? No, but what I've seen are some 20 foot lengths of rebar where you have a bar like this, and then we splice it with another bar like that, tie them together. How long does that need to be? See what I mean? We could talk about a whole assortment of stuff and bundled bars. And we don't really have time. The big point that I'd like to get across though when it comes to this development length, was that equation really that hard? Like really? It's really not. You just have to look up the factors and you plug and chug. A lot of what we're talking about with this stuff and bundling and so on and so forth is the same story. So we're not going to cover everything in this class, so you might get into a design office and somebody might ask you, well, what's that? It's not the development length, but it's going to be a very similar plug and chug expression. So just something to keep in mind. Does that sound good? Any questions?
Is that in the concrete manual?
It's in the manual and it's in your book. They have it in the book as well. It's in the textbook as to how to do lap splices and whatnot. Sound good? All right. We're sort of like at a point where there's one final topic that we kind of need to discuss, and I'd like to sort of get into it, and that's columns. Okay? Now, one point that I'd like to make with columns in concrete design tend to be pretty stout and pretty beefy. Okay? The reason why columns tend to be pretty stout and pretty beefy is the following. What was the resistance factor for beams? Like what do we use for feet for beams? It's been a while. So I guess, what was our feed value for beams? Alright, now that's the answer. Remember we had the strain in the steel that we had to determine, right? Then if we had high tensile strains, we could use a feed value of 0.9. If not, it could back off, right? Now let's go back from a behavior perspective. Why did that matter? Well, what is the difference between a tension-controlled section and a compression-controlled section? Like what's the difference? Okay, all right, so tell me what a tension-controlled section is, because you're on the right track. What's a tension-controlled section?
The steel's already yielded.
The steel yields first, right? What about a compression-controlled section?
Concrete yields first.
Well, concrete doesn't yield.
It breaks.
It crushes. There we go. What's desirable? Tension-controlled or compression-controlled?
Tension.
Why?
It's more predictable.
Well, I don't know about predictable. I wouldn't use that word.
You set
Time to know before it actually
You got time. In other words, a mechanical way to describe what you're talking about is that a tension-controlled beam is more what? I'm talking about a mechanical property. How about the word ductility? That's a mechanical property I'm talking about. Tension-controlled beams are ductile. Compression-controlled beams are what? Brittle. And when things fail brittly, they fail like that. Here's the thing when it comes to columns. Is there any tension in a column? No, it's just being pressed on. So, the best case scenario for a beam is that phi equals 0.9. But for a column, phi is pretty much going to equal 0.65. All right? Now, there are cases, and this is going to become clear in a second, where phi can be 0.75, and you'll see the difference and understand why. But by and large, phi values are demonstrably lower in columns than they are in beams. As a result, that's basically saying we're cutting the amount of usable capacity that we can use. As a result, columns are big, okay? And the result of that, we don't really have to consider buckling for most practical column scenarios. There are instances where we do if you have a fairly slender column, but a lot of times in concrete, we can ignore it. I'd say if you were designing like a 10-foot or 10-story tall building, yeah, you'd have to consider column buckling. But for simple like bridge piers and whatnot, you know, considering how big they are, probably not. Actually, not really. Now, I'm going to use the term column pretty substantially when we're talking about this, but I do want to be clear that there's two different types of members that we're going to be talking about. We're going to be talking about members that are being pushed on, but we're also going to be talking about members that are being pushed on and bent at the same time. There's a very practical example for that. If you have a building and it gets hit with wind, well, it's got to hold the building up vertically, but it's being hit laterally. So it's going to be loaded axially and bent at the same time. So when I use the term column, I'm generally going to be referring to a section that sees only axial load, whereas a beam column is seeing both axial load and bending. So we're going to take the purely axial load case first, and then do axial load plus bending moment later. Now, starting off, no bending. If we have time, we'll discuss the effects of buckling. But the way that we handle buckling in concrete design is very similar to how we handle buckling in steel design. Pi squared E, KL over R squared, you know, the alignment charts, it's all the same stuff. It's all mechanics, so it's no different. So for now, we're ignoring buckling and we're ignoring bending. So how do we compute the capacity of a short column? It's pretty simple. It's 0.85 FC prime times the area of the concrete and Fy times the area of the steel. And that's it, okay? So before we get into the math, I'd like to discuss the two types of columns that we primarily use in reinforced concrete structures, and that's a square column and a circular column. Although I actually don't really care so much about the shape of the column. I mean, it matters. It obviously matters from a capacity standpoint, but the shape of the column is not really what dictates the behavior of the column. What really dictates the behavior of the column is this transverse reinforcement. See, with a circular column, we have a bunch of bars going, you know, up and down the length of the column, and then we have this spiral reinforcement that goes down like this, okay? Whereas for a square column, we have bars going up and down the length of the column, and we just tie them, you know, we sort of like these loops that go around like this. Like square columns, the transverse reinforcement is much more akin to a stirrup in a beam, as opposed to a circular column where we use this spiral reinforcement going up and down the length of the column. Does that make sense? Okay. The shape of the column doesn't matter as much as what's going on with this transverse reinforcement, because this transverse reinforcement is really what affects how the column behaves during failure. Now, what ends up happening is that circular columns are primarily reinforced spirally, and we use ties for square columns. But I just want to make sure that you're clear that what counts is the type of transverse reinforcement. You'll see why here in a second. The long and short of it is how the transverse reinforcement serves to confine the core of the column. I'm going to sort of gloss over this for now because I got a really good picture that explains it later, much better than anything I could draw on board. So I'll just leave it at that. Now, how do you determine the capacity of a column? It's really simple, okay? All right, we compute the theoretical capacity, which is 0.85 FC prime times the area of the concrete and Fy times the area of the steel. Now, why does this equation look the way it does? Well, if I have some column that looks like this, that is the worst square I've ever drawn in my life. That is absolutely horrible. Hold on. That's a little better. That's better. Okay, so here's a column. Let's say it's 12 inches, 12 inches. And I have a bar here, a bar here, a bar here, and a bar here. And let's say they're number 9s. So I have 4 number 9s. What's the area of a number 9? We just did this. So what's the area of of the steel for this column? So that's the area of the steel. What's the area of the concrete?
12 minus 4.
Say it louder.
12 by 12 minus 4.
It's the area, the gross area of the column minus that 4, right? So we would say it's the gross area of the column minus 4 square inches. So the way that we compute the theoretical capacity is we take 0.85 FC prime minus or times the area of the concrete, which is the gross area minus that, plus Fy times the area of the steel. So do you understand why the equation is set up like that? Okay. Now, we then compute the nominal capacity. Now, what we do for the nominal capacity is we take this and we reduce it a bit. And the reason that we reduce it is we're assuming that, if you have a column and that's the centroid, that the load goes right through the centroid. All right? Who are my folks that were on the steel bridge team? Let me ask you a question. When you draw something up, does it ever come out exactly the way you drew it up? It's always different, right? Nothing that you draw up on plans comes out perfectly on site. There's always stuff that you fix in the field and stuff that gets changed. Maybe that load is a little bit off center. Maybe that load's a little bit off. Accidentally eccentric from the centroid. If that load's off a little bit, you're applying more load to this column than you intended. So we reduce the capacity a little bit to account for that. Does that make sense? The last thing that we do is we adjust for feet. Okay, so the capacity of a column is as follows. We take the theoretical capacity, we adjust it by this term alpha, and then adjust it by phi. Okay? Now, if you look at the values, what you find is that the phi value for a tied column is 0.65, for a spiral column is 0.75. The alpha value for a tied column is 0.8. The alpha value for a spiral column is 0.85. In general, spiral columns just perform better. Okay? They just perform better. There are issues, however, with using circular columns. Anybody ever done any sort of carpentry work or any sort of construction work with trying to attach to stuff that's round? You don't have a square edge to work off of, right? So it's kind of tough, So in general, you're going to use a spiral column when there's a reason to use a spiral column. One of the biggest reasons is earthquakes. Spiral reinforcement tends to confine the column a little bit better. With that, I got a lot of details that I'm going to get into, and I don't want to discuss that today. We already had a big day of details with Development Link. We can discuss this on Monday. So today, we're going to stop with this. This is the expression for the axial capacity of the column. Then we're going to say, all right, let's take this expression and let's look into the checks. There's a lot of nitpicky little checks with concrete columns that we're going to have to go through. They're not hard. They're just little nitpicky things. With that, that's all I got. If you're not in steel design, y'all have a wonderful